In note 6.4, we're going to learn what the graphs of sine and cosine look like, the parent functions, and then how to graph general graphs of sine and cosine. To do so, we are going to begin with our knowledge of the unit circle and then take that knowledge to figure out what the graphs look like. So up in the top right corner, I have drawn in the first quadrant of the unit circle. And we're going to use that to get values for the graph of sine. So x is going to be our angle and sine x is going to be our y value. So I'm going to choose values from the unit circle. So I'm going to start with 0, and I'm going to do these in radians. 0 radians. And if I look on my unit circle, when my angle is 0, the y value of the ordered pair on the unit circle, 1, 0, is the value for sine. So when the angle is 0, sine of 0 is 0. I'm going to go to my next value on my unit circle, and that's going to be pi over 6. At pi over 6, the sine value is 1/2. I'm going to go to the next value, which is pi over 4. The value of sine of pi over 4 is rad 2 over 2, and that decimal approximation is about 0.71. I'm going to go up to pi over 3. Pi over 3 has a sine of rad 3 over 2, and the decimal approximation of rad 3 over 2 is 0.87. And then I'm going to go to pi over 2. Sine of pi over 2, the y-coordinate up here is 1, so sine pi over 2 is 1. And now I'm going to continue into the second quadrant. So I'm going to use an angle of 2 pi over 3. Sine of 2 pi over 3 is the same coordinate here for the y value as rad 3 over 2. And in quadrant 2, y is still positive, so the sine of 2 pi over 3 is rad 3 over 2, which is about 0.87. The next angle I'm going to choose is 3 pi over 4. The sine of 3 pi over 4 is rad 2 over 2, looking at this coordinate, but thinking about it in the second quadrant, it's still positive. That has a decimal approximation of about 0.7. Next angle I'm going to pick is pi. The sine of pi is 0. And now I'm going to pick fewer points, because once we see the general shape, we don't need so many points in between. I'm going to pick 3 pi over 2. Sine of 3 pi over 2 is -1. And sine of 2 pi, we're going back full circle, literally, is 0. What we're going to do now is we're going to graph these points. So we're going to put the angle along the x-axis and the value of sine along the y. So this is going to be sine x is going to be our y-coordinate. And I want to explain the horizontal scale. So each line on the horizontal scale is pi over 12. So I'm going to count by pi over 12. So here I'm at pi over 12. The next one is 2 pi over 12, which simplifies to pi over 6. The next one is 3 pi over 12, which simplifies to pi over 4. The next one would be 4 pi over 12, which simplifies to pi over 3. I'm not going to put a point at 5 pi over 12. I didn't put the value there because that's not a unit circle angle. The next one would be 6 pi over 12, which simplifies to pi over 2. I skipped 2 lines. That gives us 8 pi over 12, which simplifies to 2 pi over 3, dividing everything by 4. And then 9 pi over 12, which we divide everything by 3, we get 3 pi over 4. And then we have pi, 3 pi over 2, and 2 pi. So that's how the scale works, and it's going to be important to be able to count that way once we determine the units as we go forward. Okay, so now I'm going to plot these points. So when the angle is 0, sine of 0 is 0. When the angle is pi over 6, sine of pi over 6 is 1/2. Notice that 4 lines on the vertical scale is 1, so 2 lines is 1/2. Pi over 4 is 0.71, so that's a little less than 3 lines up. Pi over 3 is 0.87, so it's somewhere up here. And pi over 2 is 1, so we're going to graph that. 2 pi over 3 is 0.87, so it's kind of midway between the third and fourth lines. 3 pi over 4 is 0.7, and pi is 0. 3 pi over 2 is -1, and 2 pi is 0. And then I'm going to connect these with a nice smooth curve, And make sure that you're not drawing pointy curves like an absolute value sort of shape, but nice rounded curves. And this would also continue in the negative direction. Negative pi over 2 would be -1. So when we draw the graph of sine, you have nice rounded curves. You put arrows at the end because the graph continues on forever in that pattern, that periodic fashion. When we graph sine, you're going to put 5 key points per cycle. I'm going to circle what the key points are in this first cycle here that we have. So key points are going to occur every quarter period. So I'm going to write that here. Key points occur every quarter period. That's the same for every graph, sine graph. In this case, 1 period is how long it takes to complete 1 full cycle. So this, what I'm highlighting here, is 1 full cycle. And it's important that you can identify 1 cycle. So 1 cycle takes 2 pi along the x-scale. So from 0 to 2 pi. So for our graph, key points are every 1/4 of a period. So that's going to be every pi over 2. And those are the points that I have circled, those ordered pairs, and they correspond to relative maxima and minima and points where the graph goes through its own axis. We're going to talk more about that in the future. Okay, the next thing we're going to do is we are going to analyze the graph of sine. So just like we've done in the past, we're going to talk about domain, range, amplitude. Well, we have a little bit of new vocabulary. So what's the domain? Domain are all x values. In this case, we don't have any restrictions. So the domain is all real numbers, so -infinity to infinity. The range is a set of all outputs or all y values. In this case, the range is from -1 to 1 inclusive, so use square brackets. The amplitude. Okay, so amplitude is terminology that has to do with periodic functions for like sine or cosine graphs. So the amplitude is the distance from the midline to the maximum. So I will write on here. So this is the midline and this is the maximum, or from the midline to the minimum. So this would be a minimum, or it's 1/2 the distance between the minimum and the maximum. And that's going to be defined later in our notes. So the amplitude in this case is the distance from the middle to the maximum. So here it's going to be 1. And if we want to change that on our graphs, we can have a vertical dilation, or that's a stretch or shrink. So dilation means both stretch or shrink. The period. The period is how long it takes to complete 1 cycle. We talked about that already. That's 2 pi. And in order to change the period, we would have a horizontal dilation. That would be a horizontal stretch or shrink. Okay, intercepts. So where is the y-intercept? The y-intercept for this graph is right here. And as an order pair, that's going to be 0, 0. X-intercepts, where does this graph cross the x-axis? So I am going to list a few, and then we're going to figure out a general expression to encompass all of them, because this graph goes on forever. I'm going to list a few. So we have 0, 0. The next one would be pi 0. The next x-intercept would be 2 pi 0. And if I envision this going on, it would keep going on until n pi comma 0, right? It can keep adding. So to get from one to the next, I add pi. So the expression for all x-intercepts are going to be n pi 0, and n is an integer. You need to state what n means. It's not just a real number, it's an integer, which means we could also go back to -pi 0, like n could be negative as well. Okay, how do I write an expression for all the maxima? So I'm going to circle, we only have one maximum point shown here. So maximum point that we have is pi over 2, 1. But to get to the next maximum, I would add a full period, which is 2 pi. So if I add 2 pi to pi over 2, I'm going to actually adding 4 pi over 2, so I'm going to get 5 pi over 2, comma 1. And then I'm going to add 2 pi again, so I can get 9 pi over 2, comma 1. And I can continue on in this fashion. So I want to write an expression for all of these values. So the way to do that is pick a starting one. Pi over 2 is the one I chose. You could choose any one. And then what do we add to that? We add a multiple of 2 pi. I'm going to add 2 pi n. And it's an integer multiple of 2 pi. That's the x value, and the y value is going to be 1. And then we need to comment that n is an integer. All right. Next thing that we want to talk about is ordered pairs for minimum values, or minima. So I've got one minimum here. Its ordered pair is 3 pi over 2, negative 1. Oh, I actually have another one. I have negative pi over 2, negative 1. To get from one value to the next, we're adding a full period, which is 2 pi. So to get the next minimum value, I would add 2 pi to 3 pi over 2, which is 2 pi is 4 pi over 2, so that will become 7 pi over 2, negative 1. And if I want to write a general expression, I can pick one value. I'll pick 3 pi over 2, and to that I'm going to add a multiple of 2 pi because the relative minimum values occur every period. So plus 2 pi n, that's the x value. The y value is negative 1, and n is an integer. In terms of symmetry, is this function even, odd, or neither? We talked about this in terms of identity, so we've done this before in a different context. But in terms of symmetry, if a graph is even, it's symmetric with respect to the y-axis. If it's odd, it's symmetric with respect to the origin. So looking at this graph, let's say I take the point pi over 2, 1. If I reflect it over the x-axis, over the y-axis, I'd have negative pi over 2, negative 1. So this graph is odd. So the graph of sine, the parent function, is odd because it's symmetric with respect to the origin.